This is Trend Following Radio, where great thinking comes alive. Nobel Prize winners, legendary traders, best-selling authors, and the pros that know what drive us irrational human beings. I am your host, Michael Covel. Not filtered, raw, honest. That's my passion.
You know, it's always a little dangerous when you get into a conversation with a physicist, one who has an especially strong knowledge of the cosmos. That's where I am today, jumping in with my guest today, Will Kinney. It's the question that when you think about the cosmos, it's the basic one. What happened before the Big Bang? Was there a before? Will does a great job of getting into a new theory about the ultimate origin of the universe. Look, this is detailed stuff. We are talking about analyzing the last 14 billion years. And believe it or not, guys like Will, they can get that detailed. It's absolutely amazing. You really have to salute the men and women who have dedicated their lives to such curiosity, to dive in, to use the best technology that we have to try to find out how the hell it all started. And like I hinted at the beginning, when you talk to a physicist, when you jump into a topic like this, your brain starts to, I'm not going to say hurt, but I tell you what, it challenges everything you've got if you're not an expert in this subject. And I'm not an expert in this subject. But I think at the end, Will gave me some kind words that I navigated him through this great topic with aplomb. Without any further delay, let's jump right into an infinity of worlds, cosmic inflation and the beginning of the universe. I hope you enjoyed this rather interesting episode with Will Kinney. I can tell in your voice, before I even get to a question, you know that your topic is dense. For the average Joe out there, which I'm one of them, even though I've been highly educated doing this podcast for a long time with many of your learned peers and all kinds of subjects, yours might be the most dense subject that I've ever attempted to bring on this podcast.
It was a hard subject to write about for that reason. It is what it is, and you have to honor the reality of it.
I could tell in your voice, we haven't spoke before, but just hearing the way that you communicate, and we'll see how this goes, but it seems like you're used to bringing people along in this topic that don't have your decades of getting into the minutia. Is that a fair assessment just by hearing your tone?
I don't know what to say other than you do your best. I do teach a lot of intro classes for non-majors and stuff, and I talk about these things to college students who are like theater majors and stuff. So you do get a little bit used to doing that sort of communication to people who aren't technical. On the other hand, the subject has a certain level of technicality to it that is unavoidable. And so it's trying to thread that needle well is hard. I hope you feel like it was successful in the case of the book.
I think I would need to probably come to multiple semesters of your teaching before I could say that I'm versed and rehearsed by any stretch of the imagination. Let me take you back in time, though, because I think this might be a good place to start before we even get into the topic at hand, an infinity of worlds. I want to know about you. Were you the savant kid or were you a grinder? Like, what was the moment where you realized, I'm going to go down this path, and this path is not going to be basic. I'm going to pick a topic here. I'm not downplaying it, but psych direction or something, or sociology direction. This is pretty dense stuff. So take me back to a point in time where you knew that the trigger had happened and you were going down this path.
I think one of the big influences on me in that regard was reading Steven Weinberg's book, The First 3 Minutes, when I was a high school student. And in many ways, this book that I've written is kind of a love letter to Weinberg's book.
Why don't you sum up Weinberg's book for those that are not familiar, including me?
The first 3 minutes was written in the 1970s originally. In many ways, it's very dated at this point. There has been so much progress in cosmology since then. But it was a book it was really the first popular level science book that talked about the actual first moments of the universe. In this case, the first 3 minutes means the first 3 minutes of time. The really transformative research that was happening at that time was understanding how the elements formed in the Big Bang. Between 1 second and 3 minutes was when the elements on the periodic table were formed. In fact, only a few of them. In the Big Bang, you only form hydrogen and helium primarily and tiny amounts of lithium and pretty much nothing else. This was a time when this was all coming to be understood. That book was about the state of the art of knowledge of early universe cosmology in the mid-1970s. It was a remarkably technical book by modern standards. I mean, if you were anybody other than Weinberg, anytime other than that, I mean, I think you'd have a hard time getting a book like that past a publisher today because it didn't dumb the subject down at all. It even had mathematical appendices that went through some of the math involved. That book really captured my imagination, was something that had a huge influence on me in terms of the direction I wanted to go when I went into college and started, because I worked on questions in cosmology, for example, for my undergraduate thesis that are still relevant to my research now in some ways. That was one of the big triggers for me in terms of picking this particular avenue to look at.
Let me keep you at that point in time, high school. Were you a really good student?
I was in high school, yeah. I was fair to middling in college in some ways, but I grew up in a rural town in northwestern Montana, Whitefish, which is a wonderful town, and I had wonderful teachers. One of the things is because it's a desirable place to live, that a lot of the people who taught in the high schools there were really good teachers. But nonetheless, it was a case of there wasn't a lot of expertise in astronomy and astrophysics to be had. You didn't have modern access to media or anything like that. I really did a lot of reading and seeking out information on my own, just out of necessity, because I wasn't getting it supplied to me in any other way.
Let me keep you at that first 3 minutes, though. Here you are, a guy in high school, and as you say, dense, might not get past the publishers today, and your love letter in Infinity of Worlds is dense as well. There's some math in there for sure. What about the first 3 minutes, though, intrigued you as a high school student that you knew? Did you really know at that moment, like, this is my life, I'm going this direction?
I was already very interested in astronomy and astrophysics in general, right? I was an amateur astronomer. I had bought a telescope and I spent time looking through it. And one of the things that I really liked in amateur astronomy was extragalactic stuff, looking at galaxies. There's something very beautiful about distant galaxies seen by the naked eye. They're very faint, very hard to see, almost like they don't exist, but your imagination can fill them out and you realize what you're looking at. So I was always really captivated by that particular beautiful thing of being able to look at other galaxies besides the Milky Way myself. Then learning how to translate that into an academic specialty or something that you can really spend a lot of time working on. Obviously, that's what you learn when you're a student, is how to take that sense of wonder and turn it into something, if you like, actionable. And one of the things that book showed me was that there are people asking these huge questions and actually getting useful answers to those questions. I mean, it was eye-opening for me. I'd never seen anything so cool before. And Weinberg he died very recently, and he was a master explainer, just somebody who could take these very esoteric concepts and make them real and alive and make you really understand what they meant.
Is there anything in particular from that book, that early experience, that early motivation, early inspiration for you? Anything in particular you might want to share now that gives people an idea of how it spurred you? I'm sorry to put you on the spot.
I have a copy of the book here, actually.
Probably dog-eared with notes, I'm sure.
I don't have my original copy. I picked up a Kindle copy recently. I very deliberately did not reread the book when I was writing mine because I was afraid of being too influenced by it. There is a beautiful quotation from Weinberg in the end matter of the updated edition. So they released several editions all the way into the 90s. He writes in the epilogue, "The effort to understand the universe is one of the very few things that lifts human life above the level of farce and gives it some of the grace of tragedy," which I just think is a beautiful sentiment. Earlier on, he writes, so talking about how we ask these questions and going back earlier and earlier in time, and he's really well aware at this time that there are these many questions that are still unanswered in this picture that he proposes. So he says, can we really carry this sad story all the way to its end, to a state of infinite temperature and density? Does time really have a stop some 3 minutes after the temperature reaches 1,000 million degrees? Obviously, we cannot be sure. All the uncertainties we met in the preceding chapter and trying to explore the first hundredth of a second will return to perplex as we look into the last hundredth of a second. From these uncertainties, some cosmologists derive a sort of hope. It may be that the universe will experience a kind of cosmic bounce and begin to re-expand. In the Edda, after the final battle of the gods and giants at Ragnarok, the earth is destroyed by fire and water, but the waters recede, the sons of Thor come up from hell carrying their father's hammer, and the whole world begins once more. But if the universe does re-expand, its expansion will again slow to a halt and be followed by another contraction, ending in another Ragnarok, followed by another bounce, and so on forever. One of the amusing things is that completely unknown to me, or maybe it was buried in my memory somewhere, the quote from the Norse mythology that I begin my book with was exactly the same one that Weinberg used in the first 3 minutes. Even though I hadn't read the book in close to probably 40 years, you can see the beauty of his writing there and the kind of wonder that he brings to these highly technical subjects. And that's infectious because it is beautiful. Trying to convey that sense of real wonder and beauty about being able to really understand where the universe came from is a powerful thing. That book really did it for me. So I felt like I was writing my book for basically myself 40 years ago, or some kid out there right now who's in an equivalent position, who's really hungry to understand how you can ask these bigger questions. Maybe someone out there will read it. It will set them on a similar path to how the first 3 minutes did for me.
Let me ask a little bit more about motivation on different topics completely. I am a guy that is motivated by the search for truth. I thoroughly enjoy that because I find often the truth, of course, as you know, in your topic area, is either hidden or sometimes when other people get involved, if there's less so in science, but in other topics, there'll be motivations to disguise the truth, structures and operations that want to hide the truth. So I've always been motivated by this search for the truth in my world and what I focus on. Is part of your motivation this search for truth?
That's what scientists are here for. We're trying to understand the truth of the world. You start from this philosophical supposition that an external reality exists in the first place, and that science illuminates that it's possible to know things at all. Certainly when I teach science, this is one of the central things that I want people to understand, is that you can actually learn things about the world and have reliable knowledge that you can use to make your existence better. That's really the underlying purpose of the scientific method. Since the invention of the scientific method, the really formalizing it that happened in the Renaissance with Galileo in particular, that idea of controlled empirical investigation of the world has been utterly transformative to the human species. There's no reason to suspect that that's going to slow down. We keep learning new things and can never tell how what you learn is going to change the world. I mean, who would have thought in the 1500s that Kepler's discovery that he could explain planetary motions by ellipses would ultimately have a domino effect that would basically be the invention of modern science and engineering and actually transform life on Earth in really meaningful ways. So that it was at that time understanding this esoteric subject of figuring out how the universe was structured might have seemed to be just an irrelevant occupation. But in the light of several hundred years of history, you can see that this actually was foundational to a lot of things that we take for granted in modern society now. Isaac Newton probably wouldn't have come up with his laws of motion without having Kepler's and Tycho Brahe's measurement and theories of the motions of the planets. But Newton's laws, of course, undergird everything about modern technological society. Knowledge itself is something that you can never predict how it's going to influence the world. Seeking knowledge and truth are simply creating a framework that you can hand to other people, and you know ultimately how they're going to use it. And that's, I think, really the power of science.
In one of my trading books, I quote the steps of the scientific method. And for a lot of quantitative traders, investors on Wall Street, they go through this process. This is part of their investing method, is to use the scientific method. It's how they do it. I mean, there's some people that just hold their thumb up to the air and see which way the wind is blowing, but a lot of people are pretty rigid about how they go about investing. Let me ask, with that setup, given that that's kind of how I look at the world too, I wish I had expended all of my energy to perhaps go down one of these really crazy, interesting paths like you. But with that setup, let me get a little controversial just on the word science for a second. And I'm not going to any particular topic area, so I would rather avoid a topic area because people just get so riled up. But it does seem like in the last handful of years that the word science has become like this hammer that people are using on each other. Instead of talking about the scientific method, instead of getting into the nitty gritty, we're either told to either trust the science or not trust the science. But instead of explaining to the average person what the process is, it becomes this political tool. For somebody like you, who, as we've just established, wants to find the truth, it's got to be a little bit frustrating to watch that in the public discourse.
I think that's true. The great physicist Richard Feynman was famous for saying that science is a belief in the ignorance of experts. It's not something that is owned by an elite caste of people and sent down to the people like religion. It's something that is, by its nature, rather egalitarian, and that anybody can learn the science. To see it framed as almost a quasi-religious thing, where it's like, we're telling you how this is and you need to listen to us, is rather contrary to the spirit of the thing, in my opinion.
It's got to be something that interesting, though, not only for you, but for your peers. It used to be, okay, we would get to some consensus on some issue, and then maybe we would learn some more information later. But it didn't seem to be a political tool that I see today.
I think there's some truth to what you're saying. Some things, you talk about the science surrounding the pandemic and things like that, that have an inevitable political dimension to them, and it's kind of unavoidable. But I think that there is wisdom in trying to keep a firewall between the scientific process and the political process. We erode that firewall at our peril, in my opinion. If everything becomes politicized, then at that point, you can no longer trust the scientific method as well. You're killing the goose that laid the golden egg, destroying the thing that allows you to obtain neutral and objective knowledge about the world.
That was how we got to where we are today.
Yeah, exactly. It's something to be treasured and safeguarded, in my opinion. Not everybody agrees with that. And so there's a lot of debate. Any scientific question, of course, is going to have a whole lot of different viewpoints associated with it. And even in something as esoteric as how did the universe begin, people bring a lot of their own philosophical baggage and preconceptions along the way. And I think that's almost inevitable. Right?
That's okay, though.
Yeah, absolutely. That's exactly why you have a structure under which you can fight these things out and actually arrive at some sort of reliable conclusion. I often say that science doesn't work because of the people doing it. It works in spite of the people doing it. We come in with all kinds of preconceptions and other agendas and things like that. But the scientific method allows us to, in a sense, transcend those and obtain knowledge that is independent of our own biases. And that characteristic of science is something that needs to be protected. Because if you don't protect that, then you don't have solid ground to stand on anywhere anymore.
Well, let's start with the first sentence in the book, because this gets right into the crux. The universe had a beginning. Like you said, this is going to cause some people to immediately want to, I don't know, burn your book, and some people to immediately hug your book. Is that a fair way to look at it?
Yeah. In fact, that sentence in and of itself is an extraordinarily controversial one. As I mentioned later on in the first section of the book, there are many cosmologists who vehemently disagree with it. That sort of forms the organizing structure of the book, is talking about the meaning of that sentence and how we interpret it and what kind of a reality it creates for us.
Why don't you clarify that in the sense that, okay, the universe had a beginning. The universe as we know it, our understanding, we can take to a point in time 13.8 billion years ago. Is that correct? I mean, we can take it to that point. Now, the debate would be, is the before and perhaps after, but for what we know about the universe, we can take it to that point in time.
That's established, I think, beyond any reasonable question. We can take the history of the universe back, and we know that the universe at very early times was very, very different than it is today. There were no stars, no galaxies, no planets, no nothing. The universe was a very smooth, very hot state, very nearly in thermal equilibrium that was gradually expanding and cooling. So we know quite reliably that the very early universe bore very little resemblance to the universe today. Our reality, the universe that we live in, definitely did have a beginning. And we've measured the age of this universe to within a few percent. So it's the age of the universe is 13.8 billion plus or minus. The uncertainty on that is about 200 million years at this point.
Is there anybody out there of a respectable nature, of a qualified mind, who's done the work, who disagrees with that? Or is pretty much your peer group on the same page?
That much I think everyone would agree about. We can, in fact, see what the universe looked like through most of its history. This is because of the fact that telescopes are also time machines. When you look out in space, you're also looking back in time because of the finite speed of light. So when I look at the sun, I see the sun as it was 8 minutes ago because it takes the light 8 minutes to get to me. If I look at a galaxy that's 100 million light years away, I see that galaxy as it was 100 million years ago. By looking further and further out, we can see further and further back in time. I frequently make the analogy between cosmologists and archaeologists. Archaeologists have to reconstruct the past from indirect clues. You dig up bones and you reconstruct what the ecosystem must have been like. Cosmologists, by contrast, have it easy because we can just look out and we can see the entire history of the universe laid out in front of us. The furthest out we can see is out to when it was about 300,000 years after the Big Bang, when the universe first became transparent to light. All of that history is there available for us to look at, and you can look at it and study it. So you can actually see what the universe was like. We can just go up, look at the sky, and you see the very earliest moments of the universe if you look far enough out.
What kind of technology are you using to see that far?
In order to see the light left over from the Big Bang itself, the universe has been expanding, and that light has been diluting and cooling. The universe at early times was full of light, hot hydrogen and helium. And when the hydrogen and helium cooled enough so that they actually formed neutral atoms, all that light that was strongly coupled to them in the early universe fills the universe. So this is the flash that is left over from the Big Bang itself. But that light has been gradually diluting and cooling because of the expansion of the universe in the 13 billion years since this was first emitted. What would have been at the time visible to the naked eye, the universe at that time would have looked like a glowing hot oven, is now primarily brightest in the microwaves, longer wavelength light, because the light has been stretched out by the expansion of the universe. So in order to see this primordial light of the universe, where you look is in the microwave. For example, if you take an old non-digital television, tune it to a blank channel and look at the static on that television, about 1% of that static is actually light left over from the Big Bang itself. It's not particularly hard to detect, and in fact, it was first detected in 1964 by Penzias and Wilson, for which they won the Nobel Prize. That was powerful evidence for the correctness of this Big Bang model of the early universe. It had been actually predicted, and other scientists, in particular Bob Dickey and Dave Wilkinson at Princeton, were in the process of building an experiment to look for this primordial light when Penzias and Wilson at Bell Labs found it by accident. They were using a big antenna to do experiments on satellite communications. Penzias and Wilson made the accidental discovery. Dickey and Wilkinson knew what it was, and they released papers together explaining this. And of course, Penzias and Wilson got the Nobel Prize, and Dickey and Wilson did not, which always struck me as being a little bit of an injustice.
Let me keep it a clarity question from the newbie me. I mean, over time, the ability to see will change with advances. I can think of, for example, the Hubble images, telescope images. What kind of clarity do we have in terms of the ability to see for you? It's your life, digging in, the research. What kind of clarity advances have we made? I mean, obviously, as you just said, as more time goes on, things are not as hot, so things are constantly changing. It's tough, but what kind of advances in technology have allowed a different clarity as time has advanced?
The technological progress has been huge. When I was a graduate student in the early 90s, and I was first going up in front of my thesis committee doing a topic defense. So one of the things you do when you get a PhD, as I'm sure you're aware, is early on when you start working on the research for your PhD thesis, you give a talk to your committee on what you're planning on doing, the general area, the kind of questions you're going to ask. At the time, this was actually, cosmology was considered something of a disreputable field. It was very data starved. There was a lot of speculation and whatnot. There was some concern from my committee about whether or not this was even an appropriate topic to do a PhD on, whether the science was mature enough to even finish a doctorate. Of course, this was right before a huge explosion of technology that allowed us, for example, to really precisely measure this leftover light from the Big Bang that took place over the next 20 years. There were satellites. The Wilkinson Microwave Anisotropy Probe, or WMAP satellite, was launched by NASA, returned its first data in around 2003. There was a follow-up mission, which was the European Space Agency's Planck satellite, that really super precisely measured this primordial light from the universe and allowed us to do things like measure the curvature of space and the age of the universe and the expansion rate and a variety of other properties with incredible accuracy. Precision cosmology didn't exist 25 years ago, and now it's really a mature and thriving field. Going forward, there's going to be all kinds of new developments as well. I mean, one of the things that the James Webb Space Telescope, for example, will be looking for is light from the very first galaxies and the very first stars. It won't be quite good enough to see the first stars forming, but it will see the immediate aftermath of that pretty well. This is one of the reasons why the Webb telescope, instead of looking in the optical like the Hubble does, actually looks in the infrared, because the light from those galaxies is so stretched out by the expansion of the universe that things that would nearby have looked brightest in the optical are actually now the light is stretched out, so it's brightest in the infrared. So if you want to see that far back in time, you have to account for the stretching of the light and look in longer wavelengths in order to see what's going on. It's one of the motives for the Webb being an infrared rather than an optical telescope. The technology development in terms of what we can see is just enormous and continuing at an incredibly rapid rate.
Before I shift you into a term that everyone around the world is hearing about and perhaps thinking about when they go to the supermarket, which is inflation. Now, you look at that word the same as I do, but you've got another way of looking at it. But before I jump into that, I want to take a side tangent. I'm not going to say I exactly prepared for this episode by binge watching old Star Trek episodes with Kirk in his Shatner days, but I did binge watch a bunch of them recently. So like I said, this is kind of a side tangent before we get into inflation and take you back in depth a little bit. But I'm curious, as a guy who's gone down this path, and I'm sure you've seen your share of Star Trek episodes or Kubrick's views and whatnot, tell me your perspective, how people in your world have advanced in their search for life beyond us, life beyond this planet.
Yes, I have watched a lot of Star Trek. I've probably seen every episode of the original series close to 20 times.
I guessed right.
Yes. Well, that's not uncommon among people in my line of work. But in terms of the big questions, where did the universe come from? What was the origin of the galaxy, the solar system? What was the origin of life? By understanding origins, you can also start to ask questions about how you're going to look for life elsewhere in the universe as well. All of these questions about where we came from are all wrapped up together. The question of where we came from, if we find other life out there, well, I mean, that'll be transformative in terms of understanding our own origins. And I think that's one of the reasons why we're so interested in doing it. Honestly, one of the most exciting fields in astrophysics right now, if I were starting my career over again and looking for some interesting problems to work on, I think I would probably be doing exoplanets. The first planetary system beyond our own was only discovered in 1991. In the intervening time, the discovery rate has just exploded, and now we have tens of thousands of known other planetary systems. In fact, we have now established pretty conclusively that planetary systems in our galaxy are extremely common and come in a wild variety of shapes and sizes and outlays. How big the planets are, how they're arranged around the star, much more diverse than I think anybody expected to find. We are on the cusp of now, we're taking the first steps to actually be able to start to look at these planetary systems, isolate ones that might be of interest for looking, for example, for life like us, which may be only one very narrow way that life can exist in the universe. But at least we know one example of it. Some proposed telescope missions for the next 20, 30 years are to actually image these exoplanets to a degree where you could, for example, measure the gas concentrations in their atmosphere and look for signatures of life or even possibly technological life. That is going to happen, if not within our lifetimes, within our children's. I think it will be really have an enormous influence on human culture in general if we really start to see evidence for the existence of life on other planets. I think it's going to change the way we view ourselves very fundamentally.
Well, you can see why I bring up Star Trek. You binge watch 10 episodes in a row, and it's like every episode is about almost exactly what you just said.
The alien life probably isn't going to look like people with pointy ears. It'll probably be quite exotic. But obviously, given the budget that they had at the time, they did their best. All we know about life on Earth today is that it fills all sorts of wildly implausible niches, things that a long time ago, environments that people would have figured were lifeless, around vents on the bottom of the ocean and highly acidic environments and so on, are all teeming with life. At least what we found about life on Earth is that it is much more diverse and much hardier in existence in more environments than we might ever have believed possible. My guess is that when we start to be able to look at life outside of Earth, we're going to find that it's even more diverse than we ever imagined in terms of how it survives and the environments it lives in. I think it's going to be very exciting and full of surprises. This is all guesswork at this point. We really don't know because we only have one example of one planet with life on it, and it's very dangerous to try to extrapolate that out to other worlds.
Let me take you back to that opening salvo. The universe had a beginning. What in blazes was before the beginning, as my father would say to me? One of those Catholic guys that was at the boarding schools or something where these debates were had vociferously, these religious debates, so to speak. His son looks at it a touch differently. I don't need to know. It doesn't make me lose sleep that I don't know. I'm probably much more in the scientific method space. I don't need to have a faith about what happened at the Big Bang or before. But let's talk about before for a moment, at least what we think we know about before the Big Bang so far.
The words get complicated. The standard Big Bang cosmology of the 20th century, the universe starts from a point of infinite density and infinite temperature called a singularity, where we can reliably calculate exactly at what point our known laws of physics break down, and we have to fill it in with something new. In the standard cosmological model, this initial singularity and the hot initial state of the universe are the same thing, and so we call them both the Big Bang. Modern cosmological theories like inflation separate those two. So this initial moment, whatever the universe came from initially, and that super hot state that we call the beginning of our universe are now separated. They're two different questions. When you say the Big Bang, you can mean one of two things. You can either mean the very hot, dense state out of which our universe arose, which we know happened 13.8 billion years ago. There's not much question about that. But the question of the initial state, the initial singularity, now is a different one altogether. In fact, that initial singularity can have happened much, much, much earlier than we ever suspected. Trillions, quadrillions, quintillions of years before that, we don't really even know. The theory of cosmological inflation is what allows you to make that separation. So inflation is really a theory about what happened before the Big Bang in the sense of the hot thermal equilibrium state of our own universe, that beginning state of the universe we live in. Inflation precedes that. But what you can also find is that there's now the question of, does inflation allow you to dispense with any initial state for the universe at all, any first cause? Or is that first cause simply displaced further into the past? And this is one of the big questions that we're struggling with right now as cosmologists. And it's a very old question. Maybe I can talk a little bit about the philosophical underpinnings of this in terms of when I was writing the book, I was reading a lot of Giordano Bruno. Bruno was an Italian Renaissance scientist, mystic, and scholar who was ultimately burned at the stake in February of 1600 on Campo di Fiore in Rome. And if you've ever been to Rome, you go to Campo di Fiore, there's a statue of him at the place where he was burned alive. Bruno was an adherent to Copernicus's view of the universe, except that he took Copernican ideas farther than even Copernicus dared to. And he realized, this was something that he, of course, stole from earlier philosophers, in particular the Epicureans, that if Copernicus's ideas were right, that the Earth has no special place in the cosmos, then the natural conclusion of this is that the other stars are other worlds and other planetary systems, and they'll have other civilizations, and that this goes on essentially infinitely without bound. The title of the book, An Infinity of Worlds, is actually a quote from Giordano Bruno. Bruno's concern, you're talking about theology, with two questions. One is this idea of an infinity of worlds, and in particular, where God lives if the universe is infinite in extent. Because in the previous Ptolemaic picture, there was a place where heaven was. It was in the Empyrean realm outside of the primum mobile, the outer sphere that was the source of all motion. Bruno was stuck with a theological question of, if you get rid of the Empyrean realm, what do you do with God? Where do you put him? The second question that Bruno concerned himself with was the question of the first cause. This goes back to Aristotle, that every chain of cause and effect has to have some previous cause. If you follow that all the way back, Aristotle reasoned there must have been some first cause to the world. Bruno, his brilliant thing was he realized that these two questions, the question of the first cause and the question of the infinity of worlds, were related to each other. Taking a Copernican viewpoint on this could provide a resolution of sorts as how you dealt with this logical conundrum of there having to have been a first mover, which Thomas Aquinas, for example, equated with God. And these problems are still with us now. That first cause is this initial moment of the universe, this initial singularity. Is it still back out there, or can you get rid of it completely? Is our universe, the universe that we see and can measure, is that isolated? Is it singular, or is just one of many? Inflationary cosmology provides a bridge between those two questions, in that typically inflation predicts the existence of a multiverse, many, many, many universes like our own, infinitely self-reproducing. And it also tells you that you can push that first cause, that first moment of being, as far back in time as you wish, but you can't get rid of it completely. So in many ways, we are seeing a modern version of Bruno's ideas being shaped in this idea of inflationary cosmology. And I think they're really philosophically very similar concepts. Bruno is the patron saint of this book in many ways, because his arguments and his viewpoint are ones that I think are very useful to creating a structure by which we understand an inflationary multiverse as well.
Let's see if I can phrase this question in a way that does not leave me looking like the kindergartner sitting down with the grad students, so to speak. I want to imagine a pebble dropping into the water and the ripples going out. I want to imagine there being borders, so to speak, to the universe. But that's not the right way to look at it, really, is it?
No. One of the great misconceptions of the Big Bang is this idea that there was, and this goes back to Georges Lemaitre with the primordial egg, the idea that the universe started out as this ball of stuff that exploded and flew off in all directions. I think that's a very common picture of how the Big Bang works. And it's completely wrong. It doesn't really reflect the reality at all. One of the things I do in the book is try to explain a better viewpoint of it, which is that the Big Bang actually happens everywhere in an infinitely large space at once. We can only see a tiny little portion of that, or observable universe, because of the fact that the universe has a finite age and light can only travel so far. So we can only see out so far because there's only been so much time for light to travel to us. And that border to our observable universe, called the horizon, is very much like the horizon on the surface of the Earth. It's not a physical place. You stand outside and you look out to the horizon and you know that the Earth exists beyond that horizon. You just can't see it. We're in a very similar situation in our universe today, is that we can only see a tiny little patch of what is presumably an infinitely large space. Inflation compounds this by saying not only is the universe itself, our universe, infinite, but it's one of infinitely many infinitely large universes that are still continuously being produced.
How do they overlap or exist within each other or next to each other?
At least in the inflationary picture, they probably don't overlap. They are all being stretched apart from each other faster than light so that you can never see one from another. There's this interesting thing, whereas if you were some hypothetical observer who was out living in this inflationary bulk, this exponentially expanding universe that is condensing into little droplets. So I make the analogy of the multiverse being like a glass of beer, where each of those bubbles in the glass of beer is a separate universe. And the beer itself is this exponentially expanding space that is pulling those bubbles apart from each other faster than light. The trick is that inside what looks like a little finite bubble from the outside, actually, because of the magic of general relativity, you can actually fold up an infinitely large universe inside that finite bubble. Each of those bubble interiors then contains the spatially infinite universe, which is all we can ever access. We can never get out of our own little bubble and see the other ones because of basic rules of causality in relativity. And this is a little bit disturbing. Basically, you're at the boundary of what you could even call science at all, because what you're saying is there's all these other universes out there that for fundamental reasons we can never see. That makes everyone a little bit uncomfortable. It's a very legitimate question as to whether you're actually doing science at all at that point, because you're proposing something that is essentially fundamentally immune from any sort of empirical test.
But that's the process. The process is to try to lay down a hypothesis about where we are, what is going on, and then, okay, this is a working path, and then to disprove it or prove it. I mean, it's what you have to do. What else can you do?
Right. And in the case of inflationary cosmology, this framework that you have actually makes a lot of predictions. And many of those predictions have been tested and confirmed beautifully. Inflation also contains, as part of it, the universe is fundamentally quantum mechanical. Inflation provides an answer to the question of where did all the structure in the universe come from? All the galaxies and planets and stuff that we see now, those were created by gravity acting on tiny little fluctuations in the very early universe, little regions that were a little denser than their neighbors or a little less dense than their neighbors. And all of those things collapsed under gravity over time, over billions of years, to form everything we see. This is our origin story. The question is, where did those initial little fluctuations come from? Inflation explains those by quantum mechanics, that these are actually a product of quantum mechanical uncertainty in the very early universe. It's a very beautiful picture, and it is very specifically predictive. Those little initial overdense and underdense regions in inflation particular form. And you can test whether or not these things match. And in fact, they match beautifully well. The point is that you have a theory that is actually very specifically predictive, testable, and we furthermore have tested it. It matches the universe that we see beautifully. So now you can say, okay, I have this real science. I'm making a very specific prediction that could be true or untrue. I go out and I look for it in the universe, and it turns out that that's bang on what we actually see. And now if I take this to its logical conclusion, I end up with this almost absurd situation of our universe being one of an infinite number of them. You just get it for free. It falls out of the theory once you write it down. That's why I say it's on the border, because there are actually testable consequences of this picture. But when you take this picture to its logical conclusion, it completely changes your picture of what the overall universe looks like on the largest scales. It's almost unrecognizable from what you started with.
Let me take you back to your explanation, where I brought up the idea of the pebble in the water, the typical way that people might think of the Big Bang Theory, myself included, some kind of initial center point, for lack of a better term. And from that moment, things expand out. I'm not sure, maybe the audience got it. I didn't get it. I want to allow myself a visual of what, if it's not the pebble perspective that is obviously incorrect. You brought up the idea of the beer bottle and the bubbles and whatnot. Maybe that's the best visual. But is there a visual that you can match with the Big Bang that corrects this idea that so many for forever have had? Is a visual?
The Big Bang in our bubble, before we get to the multiverse and all that, there's just the Big Bang itself, how the universe started out in this very hot, dense state and expanded outward. What I think is a better description is, imagine that you have a sheet of rubber or something like that you can stretch. And you draw a grid of squares on that sheet of rubber so that each square is exactly the same size as every other one. You just have a grid that you draw on that with a pen or something like that. You stretch that rubber out so that all of the squares get bigger, but they're all still exactly the same as each other. And now take your imagination a little further and extend that grid of squares out infinitely in all directions so that there is no center and no edge. This is the basis of the cosmological principle.
That's the key. No center and no edge. That's the key.
Right.
Which is a difficult concept to imagine.
Right. This is the fundamental assumption of cosmology that dates all the way back to Copernicus. I mean, Copernicus and Bruno actually were saying that the universe must have no center and no perimeter. This was known by the Copernican astronomers hundreds of years ago, and it's still the organizing principle we use to understand the universe today. If the universe really obeys these properties that we now in modern parlance call homogeneity and isotropy. Homogeneity means the universe is, at least statistically, the same everywhere in space. And isotropy means it's the same roughly in every direction. There's no preferred direction in the universe. The only way that can happen is if the universe has neither center nor edge. If I'm going to have this flat grid of squares, obviously if there's no special position in this, there can't be any edge at which this stops, because that would be a special point and you would know it if you were close to it. So now I have this grid of squares that extends infinitely in all directions, and these squares are all getting bigger with time, such that every square is identical to every other one. So there's no special point. There's no center of expansion. Everything is moving away from everything else. If you place yourself sitting in that, what you will see is that you will see yourself as stationary and everything else moving away from you. And furthermore, the further away it is from you, the faster it's moving, which is exactly what we see in the universe.
That would also apply for somebody else sitting galaxies away in their position.
Right.
The moving out from them as well.
Just like when you're on the Earth, you see yourself at the center of your horizon, no matter where you are. The horizon isn't a real thing. It's an accident of perspective. Same thing with the expansion. Everyone sees themselves at rest in the center and everything moving away from them. So now if you take this grid and go backward in time, you can use mathematics. So you can plug this into Einstein's equations for gravity and see how it evolves if you extend it backward in time. What you find is that all of those squares go to zero size at finite time in the past. This is the moment of the Big Bang. This is this 13.8 billion years ago. But even a tiniest fraction of a second after that initial moment, that initial singularity where the squares all go to zero size, the universe is infinite in extent. So this infinitely large expanding grid of squares pops into existence all at once. And that is the moment of the Big Bang. And all the way back to that moment, the universe is uniform and infinite in extent. And there is no center and no edge. This is a little difficult to get your head around, but it's a very different picture than the pebble in the water or the exploding cosmic egg.
Three-dimensional is not even the right word. When you say the phrase all directions, that's not just like, north, south, east, west. I mean, to wrap your mind around the idea of all directions, truly all directions, is a mind bender.
The three-dimensional generalization, if you like, would be to take that grid of squares and turn it into slicing space up into cubes, and all those cubes are getting bigger. So you have a three-dimensional space in which extends infinitely in all directions, in which everything is moving away from everything else. The Big Bang is a moment of infinite density and infinite temperature, but space is infinite all the way back to the Big Bang. It never gets smaller.
The energy to pull off the Big Bang, is there some way to measure that at this moment in time?
That's an interesting question. Different cosmologists have different viewpoints on it. There is one school of thought which says that what you're doing is that you are borrowing energy from gravity in order to create other things. So that the total energy of the universe, if you add it up in this viewpoint, is exactly zero. Because gravity has negative energy associated with it, you can tap into that negative energy and create positive energy so that the sum of them always stays zero. Alan Guth has made this argument fairly frequently, the guy who invented inflationary cosmology. Another viewpoint is that what you find in Einstein's general theory of relativity is that there's a loophole by which you can violate conservation of energy. Energy in the universe isn't conserved. An example of this is what we call dark energy in the universe today, this mysterious stuff that is making the expansion of the universe speed up. It acts a lot like what Einstein called a cosmological constant, or an energy density of empty space. Einstein, when he introduced this idea of a cosmological constant, it's actually an energy that's associated with empty space itself. But if you think about the expansion of the universe, you're creating new space out of nothing. You have a box, and that box gets bigger and it fills up with space. We don't really understand how we can create space out of nothing, but apparently we can. As that space gets created, dark energy or a cosmological constant tell us that if that empty space itself has energy, as you create space, you're actually creating energy out of nothing. This is, in fact, the process that drives inflation, is that if empty space itself has an energy density, what happens is it tends to drive the expansion of the universe faster and faster and faster until it's expanding exponentially quickly. And this is the fundamental physics underlying inflation itself. But what you're doing is you're creating energy out of nothing. It's not coming from anywhere. So you're violating the conservation of energy right off the bat. It's this latter viewpoint, just saying that we can get rid of conservation of energy under certain circumstances, that I think is a more useful one, trying to do the detailed accounting of the total energy of the universe being zero. Different people will disagree about that. There are a number of viewpoints.
I think, like myself, I think the audience could probably see where it could be quite fun to keep peppering you with questions and get these explanations for us novices out there. But it is fascinating. I do have one last question, and this is, as I listen to you lay these scenarios out, obviously you're just getting us newbies a little wet behind the ears here. But if I look at this number of 13.8 billion years ago, the moment, the Big Bang, why wasn't it 2 billion years ago? Why wasn't it 5? Why wasn't it 100 million years ago? Why was it 13.8?
That's a very interesting question.
I'm quite proud of myself because you're a tough cookie, okay? So the fact that you just told me I asked a very interesting question, was an honest assessment, I'm like, okay, I got a brownie point. Damn. Okay, good.
No, it's a very deep question.
Okay.
Because we are living at a particularly weird point in cosmic history, where we are in the middle of the transition from the universe gravitationally being dominated by the matter and radiation in it, the dark matter, the atoms, the light left over from the Big Bang. Those things dominated the dynamics of the cosmological expansion up until about a couple of billion years ago. We are living in this transition to the universe at late times is going to be completely dominated by the dark energy. In fact, if dark energy really is an energy of empty space, the future of the universe is that all of the things that we see in the universe now will, a trillion years from now, be expanding away from us faster than the speed of light. They'll be outside of our observable universe. We won't be able to see them, and cosmology will be impossible. We'll be one galaxy alone in a completely empty universe. So we happen to be living at this Goldilocks moment where the universe is making this transition into a dark energy dominated universe. Why are we living at this super special point when it's possible to even learn all of these things? If we lived 10 billion years ago, when the universe was only a few billion years old, we would never be able to know the existence of dark energy. If we're to live a trillion years in the future, we would not be able to do cosmology at all. We would be in an empty universe. And we happen to live at this very special moment where it's possible for us to ascertain the nature of the universe. And there's no good reason for that. It's called the cosmic coincidence problem. There are various names for it. Nobody really knows. Nobody knows why it is that life evolved on Earth at this very special moment, and whether that makes us special or not. A Copernican viewpoint would be that we're not special in any way, but there's a lot of arguments that surround sort of something about our special nature as cognizant or as thinking beings in a universe that we're capable of understanding that in some sense makes us special. And this tension between what's called these anthropic viewpoints, that humanity is in a special position, and this Copernican viewpoint that we're in some sense completely ordinary and unremarkable, is a very hot debate in cosmology right now. As you know from the book, I certainly take a particular viewpoint on that. MIT Press came and asked me to write this book, and they wanted, a 40,000 word explainer on inflation, and they got a 47,000 word manifesto on Copernicanism. I strongly want to take the Copernican viewpoint, this idea that if the universe is to make any sense at all, it must be in the context that we are, in some sense, ordinary, not special at all, and that our existence itself doesn't have any particular significance. But we do happen to coincidentally live at a weirdly special time. So how do you jive those ideas? It's complex. There's a lot of questions left to be asked.
So it does give the theologians, it gives the religious folks out there some ammunition, I guess.
You end up bumping up against religious and philosophical questions automatically in this line of work, and there's no avoiding it, even if you want to. That makes a lot of scientists very uncomfortable.
As long as we established early on here in this conversation, as long as we all stay in a search for the truth, then we're all okay. I don't prefer to be in a dogma space where I must believe this because I just must believe it. I prefer to be open-minded and let the data come in, let the evidence come in. Let us all make judgments then.
It's remarkable in and of itself that it's possible to understand as much as we do about the origins of the universe. You think about simply that fact that we can actually scientifically learn about the first hundredth of a second, the first minute, the first billionth of a second of the universe in a reliable, testable scientific way. It's astonishing.
It's fascinating as hell, right? I could keep peppering you. The book, In an Infinity of Worlds, Cosmic Inflation, and the Beginning of the Universe. You are in the deep end of the pool, my friend. This is cool stuff. I'm sure everyone listening, maybe there's some people listening that have some expertise in the field, but I think you spur people to be like, hey, instead of like watching the latest TikTok video, even though she might be cute, you kind of spur people to say, wow, might be a real path to take here to kind of re-jog my brain, so to speak, and go down a path of learning and exploration. And you're surely on that. So I salute you for going down the direction.
It's amazing stuff. And it's wonderful to be able to share it with people, open people's eyes to just how different our viewpoint of the early universe is from the stereotype of how people think the Big Bang works and some of the really interesting questions that are being asked in 21st century cosmology. So yeah, the book comes out on April 5th. You can pre-order it now at any of your favorite booksellers. It'll be available globally. And I hope that it has some influence on people in much the way that Weinberg's writing did on me when I was beginning my path as a scientist. Nothing would make me happier.
Will, people can find you easy enough on the web up there in upstate New York. Where would you like to direct people? Is there a website you want to send people anywhere? Twitter? Is there a place that you hang out a lot, or do you want them to not come beat your doors down?
I'm on social media a lot. You can follow me on Twitter at WKCOSMO. I give a lot of public talks locally and so on. And one good place to find me is on Twitter, and buy the book.
Will, cool stuff, man. I appreciate it.
Thanks very much for having me on. This has been really interesting and fun. You've asked a lot of really very deep questions. It's interesting to have the discussion.
I see a time when those awake will understand how to make money in up, down, and surprise markets. Whether new trader or experienced, college student or financial advisor, protecting against a crash or just trying to make a lot of money, trend following offers everyone an answer in uncertain times. To get started immediately, send me an email, michael@covel.com. I will send you the right trend following steps to take along with my free video. But if you want to buy and hold, trust the government and trust Wall Street, this is absolutely not for you.